All right, good afternoon. So I hope you can, so raise your hand if you can hear my voice, because apparently I have some technical issues here. So, okay, so good. So, so put your hand down. Okay, so everyone can hear my voice. Great. So we were previously have some like technical issues and looks like it's resolved. Okay, so let's start. So, let's see. Okay, so, previously, so during this period of time, all we are talking about is actually how to implement a processor that supports the MIPS instruction set architecture. So but it's really important for us to begin with the stuff like how an instruction is really executed. So first of all, we have to fetch it from the instruction memory, and then we have to decode it, we have to execute it, we have to access the memory if necessary, we have to write back the data and update the PC at the end. However, there are several ways to implement the processor. So it turns out that we are now on the same page for that. We know pipeline processor is probably the most efficient design to support the execution. So the basic idea of pipelining is that if everything goes smoothly, then on average, we can output an instruction per cycle. However, we also learned that because there are pipeline hazards, structural hazards, meaning that we have conflicts or say race conditions on the same hardware unit, or we have the control hazard, meaning that we don't know what's the next PC, so we cannot proceed. And finally, we are talking about the data hazard, meaning an instruction that depends on the result that's not yet generated or propagated when the instruction needs that. So this question tell you guys about like, okay, these are all the situations that you might be interfacing when you are dealing with your instructions. So structural hazard, we said the best way is probably modify the hardware, because the limitation essentially comes from the fact that because the hardware doesn't allow concurrent access of instructions. So two things we have done. One is like write first, read later for a register file, so that we can allow write back and instruction decode stage to concurrently working on the same instruction. Different instructions. And all instructions need to go through exactly the same number of stages. So even though some instructions, they don't need the memory stage, we cannot skip them. Otherwise, we will have structural hazard. So regarding data hazard, it's coming from the fact we have data dependency. And here, please pay attention to this, because I just caught an error on the TA slides when somebody post the data dependency issues on Piazza. So the only true dependency that should be counted as data dependencies is the output of an instruction is the input of a later instruction. So the TA taught a lot of like right after write or right after read. So they aren't even an issue in MIPS 5-stage pipeline processor. We will talk about that later. And even though the other two that the TA mentioned in her discussion session may cause issues for a later or say modern processor design, but they are still not counting as true data dependencies. So when we talk about data dependencies, when we talk about true data dependency, the only type of data dependency is the case where the output of an instruction is the input of a later instruction. So that's the only data dependency we should be counting. Listen, that's the only type of data dependency that we should count. And anything, so data dependency is the source of data hazard. However, not every data dependency would lead to data hazard. So that depends on your hardware design. So for this question, if you look at the data dependency, as I said, the data dependency is depending on the output of a register, the output of an instruction is the input of a later instruction. So if you look at the output of instructions we have, only the T0 of low word and and add immediate and branch not equal, they are the output. So anyone who is depending on them, any later instruction is depending on them. They are they will create a data dependency. However, other than that, it's not a data dependency. So a lot of you saying about like store word, but this is a source. This is also a source. Okay, so Harris, let me see. Oh boy, this interface sucks. Oops. Where is my? Oh, here we go. Okay, Harris, how can I help you?
So for save word in this example, it uses the address at A0, right?
Yeah,
and
but A0 address at A0 is the value of the memory address.
Right, but so for example, in pipelining, it would still be an issue in the sense that add intermediate, what is it? You can't change the value of A0 until after the saving has occurred, right?
No.
How so?
Because if you go back and look at the pipeline design, right? We already got the value of register here and we propagated it through. So even though you modify anything you modify after this point doesn't matter, doesn't affect the correctness, right? So the case you mentioned is not an issue at all.
Okay, so that would not be a data dependency.
Yeah, so even though there's no data forwarding, there's no issues here. Okay?
Okay.
All right. Okay, Byron, question?
I think I heard you earlier say that A0 and save word is a source as well. Did I hear that correctly?
Yes. Yes. So both A0 and T0, they are sources. Because, okay, so store word means that we are storing data into memory address A0 plus 0. So we are not storing to A0. In fact, we need A0 as the source of computing the effective memory address.
Oh, okay. And that memory is going to be the output.
So it's a source, right? And we are not storing into A0. We are storing into memory address of A0 plus 0.
Okay.
So
got it.
A0 is completely a source. It's not even a target.
Okay.
Okay.
Makes sense.
Cool. All right. So this is the so if you look at the pipeline design, the original pipeline design without data forwarding, then everything here every data dependency here would become a data header, right? So we talk about data forwarding. So the basic idea of data forwarding here is that as long as the value is ready, we can set the later instruction to use it, right? So so any later instruction, right? As long as the value is generated in the pipeline, we can use it. So, but when can we generate a value? So for memory instructions, like low instruction, it's ready after its memory stage. For ALU instruction, it is ready after its execution stage. So if you notice this, right? So if you look at that, well, so first of all, this is the hardware that you need to forward that. And I didn't because my class. In my class, I think for computer science students, we don't focus on the hardware design. But another thing that I want to mention is that, well, the textbook has quite a few errors in this chapter. So that's why if you are reading for this chapter, please use my slide as the standard, because like this pipeline diagram that I put, pipeline graph I put here is different from the textbook because the one in textbook will not work. But this one is a fixed one, right? So this is the data forwarding unit we need. But there are still cases, even though we can fully forward data. So look at this, right? So if this is the lower instruction in the first cycle, we can also remember, right? So right now we know there's a data dependency between them. But because for the lower instruction, we can only generate its correct outcome after the memory stage. So by no means you can proceed at this point, the later instruction before the memory stage of the lower instruction finishes. So you have to stall the add instruction for one cycle, meaning that the add instruction has to repeat its decode stage again, because decode stage is the time that we prepare the inputs for your ALU. So because add did not leave its ID stage, so store word cannot enter in the ID stage either. So that's why both of them has to stay at the same stage, and no one in the execution stage, because it's blocked by the fact that add cannot enter its execution stage, because the input for its ALU is only ready in the next cycle after the memory outcome can be forwarded to the ALU of the add instruction. So that's how you draw the pipeline. And if you are lazy and if you just don't want to understand what's going on here in the hardware, I can just tell you, load between anything after a load, if it's depending on the output, if it's an immediate instruction that's depending on the output of the load, it has to stop because the value is ready by the end of memory stage. And before that, no one can get a right result. But if you look at other instructions, like the store word instruction would require the T0 input and at its memory stage. And at that time, the add instruction is already in its memory stage, so you can forward it here, right? And then for the add instruction and the branch instruction, because the A0 is ready in execution stage, so we can forward it at a time. So somebody asked the question, how in the hardware do we have to draw the arrows to a homework to indicate the forwarding? Yes. Okay. So that's what we are expecting you to draw. All right. So with this question, you can see we still have one case. We still have one case that we need to stall. That is after the load. And because that one case, so we actually have to, in addition to the data forwarding unit, we need the data hazard detection unit like this. We need the data hazard detection unit to show you, to detect the case like, okay, if this is a memory read instruction, right? If there is an instruction called a memory read, then we would disable the update of your instruction fetch and decode pipeline register so that you will keep decoding the same instruction, and we also disable the PC write, so you are staying at the same instruction for instruction fetch. Okay, so you have to draw the entire diagram for the homework, like if ID, EX, ME, and W back. Yes, that's what we meant by the pipeline diagram. So the pipeline diagram is something like this. So you have to draw something like this in your homework. Yes. So if you didn't do that, you still have time until tonight. All right. So oops. All right. So now let's talk about okay. So I hope this part should be clear enough for you because I just noticed, well, so another reason why I'm a little bit chaotic today is because I just realized that we in our discussion session, our TA didn't deliver the right stuff to you. So I hope this would clarify. Okay, so now another question which we also mentioned in the homework is that, and so, the reason why I pulled this up because I thought you guys already have the tips that I give you in drawing the pipeline diagram. That is, that's not showing in this slide, right? So with that tip, right, what you will be able to do is like, even though I have more pipeline stages, right, that shouldn't be an issue, right? So, so some of you think about like data forwarding might solve everything, right? However, that's not that even with that, right? Like let's say like what if my pipeline goes deeper, right? So like this case, we said you have a second memory stage, right? So your memory stage is split into two, right? So saying that I have IF, ID, EX, M1, M2, right? Again, for this add instruction, it has to wait until the end of the memory memory stage to get your output, to get the right input for the add instruction, right? So that's why data forwarding doesn't really solve all the problems, and because if your hardware changes, you have to redesign your hardware, and the thing is that you can never generate the output earlier, because that's just the nature that you just have to wait, right? So so that's how you draw. So that's an issue with the pipelining, right? So again, right, if you go back and look at the data forwarding, right, there are cases that you still have to stop, because for the memory instruction, the output is just generated so late. So even though you have full data forwarding, you still have to wait, right? So and this stall would increase if your pipeline go deeper, right? So that's the stuff that we want to mention here. So a lot of you have question here. If you have question, just raise your hand, because like using the chat sometimes it would just make me a little bit defocused. So if you still have question, raise your hand. Don't use chat. If you have a question, raise your hand. Don't use chat. Otherwise, I will be defocused. All right. So, but if you don't have any other question, we will proceed. Okay. If not, then so the thing is that if you so even though I have data forwarding, right, we still cannot solve all the issues, and this was set up the stage for some topic that we will talk about in the after the midterm. But at this point, all you need to remember is that even though we have data forwarding, data dependency would create an issue, and that drives us back home for this question that I asked you guys before. So when I say, like previously we mentioned that for this pieces of a code, right, then this version is indeed slower than this one, right? But why is that? Because if you look at this pieces of a code, right, a lot of stuff, they depends on the outcome of, well, so first of all, your index is depending on the content of data index. And the next index is also depending on the outcome of the current of the index you computed in the previous iteration. So it turns out that there are so many data dependency here, and the data dependency, some of them are depending on memory instruction, and this one is depending on multiplication. So you know multiplication is longer than this, right? So this example tells you that if your code is depending on a long latency instruction, then you are creating a case like this one, right? You are creating a case like this one that that because of the long latency, so the later instruction has to wait for longer. So this is explaining why this pieces of a code, like for A version, why it is slower than the B version in this case, because you have data dependency on the computation result of the multiplication, and multiplication is still slower than shift and subtraction operation. And this is explaining to you, like, even though we have the pipeline, it won't, it still cannot resolve the long latency delay because of the multiplication. Harry's question.
Yeah, so I was just going to ask, why is it that multiplication, despite being still a single instruction in assembly language, is longer than it takes longer than the shift?
Well, that's because, like, if you think about what you learned in CSE140, right? If you just want to do a shift, then you just need to have a few mux. And mux is one of the fastest circuit that you can have in a hardware design, which usually take probably picoseconds, right? But multiplication, you have to go through multiple stages iteratively. And even though, yeah, so you will have like multiple cycles to count that, right? So the dependency chain will be really long for that one.
Thank you.
Okay, all right. So hopefully that will clarify that. Okay, so now some of you think about compiler is the king. So the question I want to ask here is that if I have the compiler to optimize, do we still have to stop for this code sequence? All right, let's wrap up in 15 seconds. Okay, everyone just voted. So, so right now it looks like it's better of an idea that we have a breakout room for discussion. But before that, as far as I remember, I should send you the screenshot. So I just send it out and open it before we start, and then right now, I'm going to put you guys in breakout rooms. So go ahead, do it. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, great. So after discussion, looks like most of you are converged to a single answer. So why don't we have some of you express your thought by raising your hand? So who like to? Okay, so I have onward.
Yeah,
What do you think?
I said E because the way things are ordered, it'll definitely affect the correctness because 1 through 4.
Okay, so what happened if we reorder 1 and 2?
So if you reorder 1 and 2, you're not actually basing T0 off of the value of A0.
Right, so T0 will be getting the wrong value, right? How about 2 and 3? Exactly,
and,
right? So how about 3 and 4?
Yeah, it's like a chain effect because you're modifying them either like loading or storing. So you're going to change the value of what A0 is going to be, which will affect
right.
the
So if you
reorder
reorder 3 and 4, that will be an issue, right? And 4 and 5,
exactly.
you cannot reorder them, right?
Yeah.
So none of this pair can be reordered, right? So here's the thing, right? So a lot of you saying that, well, having compiler optimization will solve all the issues. But in fact, is that if you try to write your code like this, then it's impossible for the compiler to do things well. So one of the examples is like, just like the previous thing that we put it here, right? So if you are creating a long latency dependency on this pieces of code, then your performance would be very bad, even though you try to use compiler to optimize it, right? So the thing is that compiler optimization has all. So there are quite a few stuff that can help address the data dependency issue, or say data hazard, like data forwarding. But as you can see here, the data forwarding does not solve all the cases, because you just cannot forward data that is generated late in your pipeline, right? So here we still have to stall. And some of you might think about, well, compiler is the king, so compiler can help on everything. But for this pieces of code, there is nothing really the compiler can help, right? So so a very important takeaway here is that, well, we can only mitigate the data dependency or a data hazard issue. However, the ultimate way is that you probably need to think about if there is a better way that I can improve the data dependency issue to allow potential compiler optimizations. And we will talk about how to do this, or what kind of technique would help us to do this tomorrow. But today, for now, we are going to talk about another very important topic that's called control hazard. So control hazard means that the case we cannot determine the PC. So I just want you to get an idea like how serious the compiler, the data control hazard would affect your performance. So let's look at, so why don't you look at this problem and give me an answer as quick as you can. Let's wrap up in 10 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so according to what I learned from you guys, it looks like we really need some discussion. So I will use the breakout room. And before you go into the breakout room, right now, please open the question that I sent out through the chat. Other than that, let's go ahead and do it. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so looks like group discussion does help. And after the discussion, most of you are converging to the right answer. So can I have some of you share what your group taught you and why do you think this is the right answer now? So I have Japong. Thanks.
Okay, our group converged to 1.4 because for the
hold on. For Harris, what does your group converge to?
We also converge to 1.4.
Okay, Danling, what do your group converge to?
We thought was 1.6.
You thought it was 1.6. Okay, for Japong, can you talk about like how your group derived 1.4?
For instructions other than branch, I would just take one. The CPI would just be 1, and 80% of them that will contribute. That will be point A of the. That will contribute point A. And for 20% of the branch instructions, it will just only need to get after the execution, so it will be 3 cycles.
Okay, why execution?
Because after execution, we don't need to.
Okay, so that's why I put this pipeline graph here, right? So what do you need to do in execution for a branch instruction?
We need to calculate the PC.
Right, the PC is right here, right? So before this is done, you don't know. And what else? What else?
What do you mean by?
So that's the PC, right? What else do we need to wait until the execution stage? So branch, you need a target address, but what else? How do I know if I
check
want to make?
a condition?
Yeah, where do we check the condition?
ALU.
In ALU, right? So you need this too. So in this case, like how many cycles it takes to execute a branch? Well, how many cycle of the delay after the branch instruction is fetched can we get the next instruction? So 2 more cycles, right? Because presumably we can fetch the next instruction here and here, but right now we can't. So the average CPI of a branch is 3, right?
Yeah.
So if you count that together, that will be 1.4.
Wait, hold on. You're saying the average CPI is of the branch is 3, but I'm not entirely clear on why is it that we need to wait cycles after the calculation has occurred in the ALU?
Because only after the calculation, you know if I'm taking a branch or not.
Right.
If the branch is taken, I will go to the target address. If the branch is not taken, I need to fetch the instruction that is PC plus 4. So only at this point, you can start fetching the next instruction.
On another point, the reason we're assuming that the CPI for all the non-branch instructions is 1 is because we're also assuming full pipelining, right?
Right.
Got it.
So this is the case, like if everything is full pipelining, right? The average CPI is 1, right? But if you look at, okay, so let's say like we have this load instruction, right? Then if you look at the load instruction, the next instruction here needs to wait for another cycle. So you can say the load instruction, the average CPI is going to be 2 here, right? Because you are only generating the outcome for every 2 instructions. If both of them are back to back, if all of them are load, right? And the same thing for branches, that you have to wait until the execution stage, right? So this is another way of drawing it, right? So let's say I have let's say like after the branch, right? At this point, I cannot do anything, right? So I can only put no ops in there, right? So you are essentially having this empty slots here. So you can think this branch instruction is essentially like 3 instructions, right? And if the effective CPI of 1 instruction is 1, then 3 instruction would be 3, right? Does that make sense? Other question? Okay.
I still have a question.
Sure.
So how do we assume that it's like full data forwarding? Like it's not
So that's why I put why I put this diagram here.
Okay.
Right?
I see.
Right. That's what I put the diagram here.
Mm-hmm.
Right.
Okay.
Okay.
Thank you.
Okay. Hi, question.
Yeah, so could you show the diagram again?
This one?
No, the structure for that the processor. Yeah.
This one?
So so you just mentioned for so for a branch instruction, if we just stop to handle the data hazard, then we need to stop to
No, there's no data hazard here.
Okay.
It's just because we have to wait the branch outcome. It's the LU result, and we need to wait for the outcome.
Yeah, so it is like yeah, so it means that we are using data forwarding, or we are using stall.
I mean, here, if there's, well, so it says we insert no ops until we can determine the PC, right? So it's a stall, right?
Okay.
We disable the instruction fetch and insert no ops. That's stall. That's the definition of stall.
Okay. Yeah. So
right.
it means that if we use the stall strategy for the branch instruction, then we need to stall for 2 more cycles.
We need to stall the next instruction for 2 more cycles. Yes.
So
because we don't know who is the next yet.
okay, yeah, cool.
Okay.
Yeah.
Okay. All right. Thank you. So those are good questions. So that's so now you know, like, okay, for branch instructions, right? Even though it's only 20% on average, it will drives up your average CPI by 40%, right? That's a big issue. That's the big issue, right? And some of you might ask, okay, why can I only stall? So that's actually the question I'm asking you. Why, for the previous question, for the given pipeline diagram that I show here, the only thing you can do is to stall. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, again, I already sent out the question through the chat, and looks like we really need some kind of group discussion. So why don't we go ahead and do it? Up in 10 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, I have seen most of you pick C, but I really want to make sure that we are on the same page for the two that we have trouble with. So can I have some of you sharing your thoughts? Okay, Tui, I miss you.
Hi, sorry about not showing
No
up.
problem. Yeah.
So my group all agreed that 1 and 3 are correct.
1 and 3. Okay, so why the branch target address is not available for the instruction fetch stage of the next cycle?
Because it hasn't been calculated
Where
yet.
is it calculated?
It's calculated in the, sorry, I'm looking for the right ALU.
This one, right?
Yeah, that one.
Okay. Okay, so how about the second statement? For branch not taken, what's the address?
The address is just +4, but we already calculated that in the ALU to the left.
Here, right? So this is
Yeah.
not an issue, right? The branch outcome cannot be decided until the comparison result of LU is not out. Is that true?
Yes.
Okay, so this one is true, right? And it's also get out here, right? So
Mhm.
how about the fourth one?
So you don't need to wait for the write back stage. You can.
And in fact, does the branch instruction write back?
No, it does not.
It doesn't change any register value, right? So this is not, right? So these are the two reasons why we can proceed without stall. So I still see Harris, you raise your hand. Thanks, Tui. Thanks for your insight. Okay, Harris, I still see you raise your hand. Question?
Yeah. Well, no, it's I just haven't lowered my hand in time.
Okay.
No, our group agrees that 1 and 3 are the true ones. So.
Okay, awesome. So we are all on the same page. Great. So the reason why we cannot proceed is just because the branch outcome is not out yet. And okay, Yizi, what's your question?
Yeah, sorry for interruption, but I just need a little bit like more explanation about like why the number 4 is incorrect.
Because for the branch instruction, we don't have any output.
Okay, so the write back is not real, right?
So again, the reason why we have the branch go through memory stage and write back is just because we want to avoid a structural hazard, right? But branch instruction can actually get its job done after the LU result is out because we don't need to access memory. We don't write back anything, right?
Oh,
but
yeah.
We have to go through 5 stages because of the structural hazard.
Yeah, the number 4 actually describes the structural hazard because
right.
When we decode, we want the last branch instruction to write back the result. So the 4 is actually a structural hazard.
Right.
Okay. Yeah. Thank you.
All right. No problem. All right. So those are good discussions, and sounds like when it's closer to midterm, you guys are really getting your mind clear now, right? So for this question, 2 of them are correct. So right now, the thing is that sometimes, right? So when we talk about midterm, right? And one thing that I can tell you is because this is an online midterm, so I will definitely, and we have a lot of multiple choice questions. We have a lot of reading quizzes, and they are all in the form of multiple choices. And you can call me a professor who really loves multiple choice questions. So how can I not having multiple choice questions in the midterm, right? So let's say right now you are taking a midterm. I don't know what's the answer, right? Then if there's no penalty, for those multiple choice questions, if you don't know the answer, what will you do? We would just guess, right? Because if you guess yes, Byron, you say guess, right? We would just guess, right? If you guess it right, you got a point. And if you guess it wrong, you didn't lose anything. There's nothing for you to lose, right? But if you didn't put anything there, you will get no points, right? Some of you saying pick C, right? Okay, so some of you saying that pick C, that's actually a static prediction, right? If you always pick an answer that you like, that's static prediction, right? So if we want to do static prediction, right, the only thing that we need to know about and if I want to do state prediction, I still have this two issue. I have to know the target address, and I have to know I have to guess the branch outcome. So if I want to do prediction by just guessing the outcome, there's no way I can predict branch taken, because the branch taken address, the taken address must be calculated, right? So the easiest thing to do is that we can predict not taken, since we don't need a target address. And for not taken is always PC plus 4. So for static prediction, it's very easy to predict not taken. So if we predict not taken, what the pipeline diagram would look like. So this is the pipeline diagram. So first of all, for the first cycle, we will be able to fetch. So what if we pick someone? I think, Tui, do you want to be the one who iterate this with us? Are you still around?
Yeah, I'm up for it.
Okay. So right now, at a second cycle, what can we do with the load?
With load, so we decode instruction.
Okay, can we fetch the add immediate?
Yes, we can.
Okay, so there's no issue, right? So how about the third cycle? Can we continue? Can we have every instruction go advance to its next stage?
Every other instruction for now.
Yeah.
Add, yes. So load, add, and add, yes,
right.
you can.
Right, because there's nothing prevent them from advance, right? So how about the next cycle?
That's true too. You can do that for all instruction.
Right. So how about the next cycle?
Let me check for the add. Is this with forwarding?
Yes. Right now you can assume that we have full data forwarding.
Let's see. Statistically predict not non-taken. Yes, you can.
Right. Because for the one that you are concerning, right? This one can be forwarded, right?
Yes.
So there's no delay here, right? But we can fetch the branch instruction as well, right? But how about the next cycle?
For the next cycle, we're still gonna fetch it, but we might have to flush stored and add. We don't know yet.
Yeah. We don't know yet, right? We don't know yet, right? So at this point, you can fetch the stored word, right? But at this point, because the branch outcome is not out yet, right? All right. So next cycle is the branch outcome. So the next cycle, when the branch finishes execution stage, right? We know, well, let's say like this one is a taken one, right? So we are going back to the low word, right? So you have to flush the store word and the added instruction, meaning that they are not going to be executed to the end, right? And fetch the right instruction.
Yes.
Okay. So thank you, Tui. I think that's a great answer, right? So if you keep drawing the pipeline diagram, you will find out, well, for predict not taken, it's working fine if most of your branch is not taken going forth through. So, but however, in a lot of cases, we have branch because we want to implement loop, and predict not taken works terribly for the loop. But there are still cases we wanted to predict taken or not, predict not taken, right? So this is statically prediction has its own limitations. But the good thing about static prediction is that, first of all, if you just statically predict not taken, right? Okay. So I have Yizi question.
Okay, so sorry for the interruption, but
no problem.
Since I think so, we actually take the branch for now. So why are we still doing the 5 stages for the load word in the lax instruction?
Which one?
Oh, sorry. I see why. Thank you.
Okay, cool. All right. So for this, So look at this, right? So right now I want you to, okay, so this is the basic concept of static predict not taken. So let's see how useful is the static predictor. So why don't you spend your time looking at this question and see how general the predict not taken will help you. All right, let's wrap up in 15 seconds. Five, 4, 3, 2, 1. Time is up. Okay, first of all, I have sent out this question through the group chat, and looks like the answer for this answer we need some discussion for sure. So why don't you go ahead and do it? All right, let's wrap up in 15 seconds. Five, 4, 3, 2, 1. Time is up. Okay, so looks like most of you are doing branch predictions. So you are thinking about the answer will be C. So can I have some of you share about the thoughts of your group? Okay, Harris.
So our group actually put down A.
Okay.
And the reason we put down A was because the if statement is not like the branch there, that's not the only branch in play. The while loop has a branch in of itself.
Okay.
And so the okay.
Hold on. So for Japon, what do you think?
I think I would agree with Harris.
Okay. So you think it's okay. So okay. So you agree with Harris?
Yeah.
Okay. Okay. So, right. So do you want to walk through the example?
Sure.
Okay. So the first time this is a do loop, right? So we will go to branch X, right? And right now we are, so forget about the state, right? We predict not taken, right? The actual result is taken, right?
Yes. Mm-hmm.
And for Y, right? Forget about the state, okay? It's predict not taken because this is not taken predictor, right? So we always predict not taken, right? Is this taken or not taken?
It would be not taken for a while loop.
Why?
Well, don't you, in assembly language, don't you set up loops to have the condition that is the inverse of?
So if it's in a loop, is it taken in a loop or not taken in a loop? Look at the previous example. If it's the loop, is it taken?
No, it would be taken.
Right. So here, right, it would be taken, right? So if you keep iterating this one, right? This time, is it taken or not taken?
Not taken.
Not taken, right? So you will repeat this pattern for you will repeat this pattern forever, right? And then you will see the answer will be A in this way, right? Because you are only get it right 1/4, 1 of the 4, right? Okay. Oh, sorry.
Yeah, sorry.
Question?
Like, yeah. Well, see, again, my group got A, but I guess we used different logic than the correct one.
Okay. Yeah,
so,
but if you list a table, it would be like this.
Right. Yeah. So taking the loop would be like repeating the loop in of itself, right? Like if
Right.
branch Y, if we took that branch, then it would be repeating everything in the dual while loop.
Yes.
Okay. Just want
Okay. Okay. All right. So we know, like, okay, for this branch predictor, its accuracy is really bad, right? So we are teaching you a better thing. That's called dynamic prediction. So every processor has a dynamic predictor now. So we have said, well, we don't have the target address, but we can make a cheat sheet of that, right? So the basic idea of a cheat sheet is that if you know how to calculate the branch address, is that it's based on the PC of the instruction plus the offset times by 4, right? So in this way, the PC is a constant for each instruction. The offset is also a constant. So once you have that instruction go through once, you can actually keep that in a buffer or say a cheat sheet that's called branch target buffer, which memorize all the target address that we have seen before. So the next time when you see that PC, it's a branch instruction, you know its target address must be that, right? And for the branch outcome, we just make a wiser guess. So we use history or states to predict that. So this is how it works. So a basic, so I simplified the pipeline diagram a little bit more. So this is the branch target buffer. So what it does is that we keep track of the branch PC. So whenever an instruction come in, I just check if this is a branch instruction. If this is a branch instruction, it has a match, and I can find its target PC here. I will look at the state to see if I should predict taken or not taken. So for this example, right, I would say for this too-big predictor, we assume if the value is greater than a certain threshold, we predict it to be taken, right? So that's the basic idea of too-big bimodal local predictor in a way that if we associate with each PC with a 2-bit counter. And this is actually a saturated counter. So this is the state machine. So a lot of you are trying to memorize the transition of the state machine or something. And that's what a lot of architecture professor would tell you to do. But all I want to tell you is that treat this state as a counter and see what's the value in there. If it's 0 or 1, then it's not taken. If it's 2 or 3, it's going to be taken. And it's a saturated counter. So if you go up to 3, no matter how much you add, it will keep staying at 3. The only thing it would make it transition, it can only go back, cannot go up. That's when you reach the top. And if you are reaching the bottom, which is the 0, then no matter how bad you are keep doing, no matter how many not takens you have, you just stay at 0. But the only thing will change its state is that you get a taken, right? So that's a saturated counter. And when the threshold is above, when it's above 2, then it's equal or above 2, you predict taken. And whenever you have a taken, you increment it. If you have a not taken, you decrement it. So that's the whole idea of maintaining the state. And if it's 1, 1 or 1, 0, you predict that to be taken. So that's the 2-bit predictor. So put it in a pipeline. What it would do is like this. So we have the PC. We use the current PC to check if there is an entry in a branch target buffer. If there is the case, we also have the target PC, and we use the state to consider what's the next instruction we want to fetch. So like this one, we know we are going to predict taken. So the next instruction we are going to fetch would be this address instead of this +4. But again, we still only know the outcome of the branch after the execution stage. So you need a feedback logic here to let you update your state and flush instructions if necessary. So that's the basic concept of dynamic predictor. So for this do while loop, right? We can see, like, for the first time, let's say, well, let's initialize our current state at 1, 0. And the first time we will predict taken because right now we are at 1, 0. However, because this time it's a take, and the actual, because this is a loop, right? So for loop, we are if you are going to take the loop and then you are going to take it again, right? So the actual result is taken, right? So when we say taken, we are going to increment the counter value by 1. So in the next cycle, you will see the state is right now going to 1, 1. We are at here now, right? And so in this time, we are still predict taken, and the actual outcome will be taken, right? And when you are at 1, 1, because it's a saturated counter, so you are not going up anymore, right? So if you keep going, you will figure out that you will repeat the same pattern, and you are only going to get one thing wrong at the end, that when we are not taken. And the next state after this would be 1, 0, because we are decrementing it because we have not taken. So that's the basic concept of a 2-bit predictor. And you can see for this loop, right? Previously, if you predict not taken, you are only going to get this right, 10% accuracy. But right now, if you have a dynamic predictor, you are going to get 90% accuracy. And if you have 90% accuracy, the CPI, the average CPI right now would be only 10% of the time you are going to suffer that 2-cycle stalls, or say the 2-cycle instructions that you have to flush. So the average CPI is only going to be 1.04, which is very, very close to 1. That's our optimal. All right. So let me see what time. Do we still have time? So why don't you go ahead and just, well, so let's try this question and see by how much you understand branch predictor. All right, let's wrap up in 15 seconds. Five, 4, 3, 2, 1. Time is up. Okay, although we are short on time, but I think it's still better of an idea that we have a group discussion this time. So I am sending out the screenshot right now. And before you start, we should have a group discussion. Okay, so open that one. So let's go to group discussion. All right, let's wrap up in 15 seconds. Five, 4, 3, 2, 1. Time is up. Okay, so now I want someone to explain your choice to all of us. Okay, Jiapeng, what do you think?
I say it's 70%, about 75% time.
Okay, how do you get that?
For the if statement, it will start at 0, 0, and the first time it gets is not taken, and it will.
But the actual taken or not taken?
Not taken.
Okay.
The actual is taken, so it will move to 0, 1.
Okay, it will move to 0, 1 later, right? But now the next is y, and is still 0, 0, right? Are we predict taken or not taken?
Not taken.
Okay, actual.
Taken.
Taken, right? So the next cycle, as you said, right now the X branch would become 0, 1. So are we predict taken or not taken?
Not taken.
Not taken. Actual.
Not taken.
Not taken. Okay, how about Y? 0, 1, predict
0,
taken,
1.
not taken.
Not taken.
Not taken. Are we taken or not taken?
Taken.
Okay. How about, but if you keep going, right, you will figure out that at some point, right, we will train the branch Y to above the threshold. So everything would be predict taken, right? So for the Y, it's roughly about 100% accuracy, right? For the X, we are going to have only 50% accuracy, right? So given the amount of branches we have, they are equally amount, so it will be 75%. Harris, you don't agree with that, or do you agree with that?
Oh, no, I absolutely agree with that.
Okay, Awesome. All right. So this is the question about the branch prediction. So so I will announce the homework later today. And before you leave the classroom, and sorry for being late because of the technical issue, but I do have a lot of stuff that I need to let you know before the turn. So that's why I stretch the lecture a little bit. But before you leave the classroom, there are a few things that I want to let you know. So first of all, plan your time carefully. Time management is important. And assignment 2 due this evening, assignment 3 due this Wednesday. Midterm, it will be Thursday during the lecture. And the lecture on Wednesday will tell you everything about everything you need to know about the midterm. And we will give a sample midterm as well. And another thing is that some of you are asking our tutors about like, can we extend the lab deadline? The answer is no, because actually, as I mentioned in the very beginning, all our lab deadlines are soft deadlines. And because this is a summer session class, remember you are taking a summer session class, we only have 5 weeks and there's no way we can extend the deadline anymore. So you just need to manage your time carefully. And again, those deadlines are soft. I mean, we still have tutors helping you on Saturday, Sunday. So we are not going to extend those deadlines for sure. And again, they are soft. So don't worry about that too much. And all you need to do is that making sure that you get the lab 5 and 6 ready by the end of the summer session, and you are all set. Other than that, enjoy the rest of your day. I will have office hours